let's establish some terminology for molecules and ions that are dissolved in water. Now, if it's dissolved, the thing that has been dissolved is going to be the solute. Contrast that with the solvent, the thing that's around it. Now, you might decide to be philosophical about that and say, well, what if I mix 50-50 by volume methanol and water? Well, honestly, at that point, the definition has gotten a bit messy. But most of the time, we're not going to be talking about something where we have similar numbers of molecules around. Now, just to give you an idea of the molarity of water, if you were to take the mass of 1,000 grams of water, that would be 1 liter, and convert it into moles, and then you were to divide it by the 1 liter that it has, you'd find out that the molarity of pure water dissolved in itself is about 55 or 56 molar, somewhere in that range. Now, obviously, most of the solutions we talk about are more like 10 molar or less. And so it's going to be fairly clear to us which one actually has the large number of molecules and which one is the small number of molecules. So yeah, there is going to be that philosophical moment where it turns into kind of a line like They Might Be Giants used in one of their songs, Particle Man. You know, talking about a particle. When he's underwater, does he get wet, or does the water get him instead? You know, in other words, is the water getting Kevin'd instead of getting wet? That's enough philosophy for one day. Now, things dissolve, and when they dissolve, we're saying that the solute has separated from its neighboring solute molecules. Good example of that, table salt, NaCl. We know what that is, table salt, and when it dissolves, we know we get the sodium ion and the chloride ion. When they're by themselves and dry, they stay stuck. What helped them get apart? Water molecules helping to pull them apart. That means that they have gone from being precipitated as a solid to being dissolved in the solution. Now, there's an extra little step to these things sometimes. Some things will dissolve but stay intact. Sugar molecules are a great example. All those carbon to carbon bonds, those carbon-hydrogen bonds, carbon-oxygen bonds, these are covalent bonds, and they're very strong. And they aren't things that we typically are going to break in fact, we aren't going to be breaking them by dissolving. About the only bond we'll break in a dissolving process, really ever, that we talk about in Chem 1, would be when an acid dissolves in water and one of the hydrogens pops off and becomes a proton in the solution. And we'll see that when we talk about acids and bases. But most of the time, we're not going to have covalent or molecular bonds breaking. What happens, though, is they will dissolve. Now, compare that to NaCl. NaCl, I said it dissolved, but it also dissociated, right? It didn't just pop loose from the neighboring NaCl formula unit and stay together as an NaCl. It popped loose from its neighbors and separated from each other. Dissolve and dissociate. Those are going to be two separate processes, and we have to make sure that we account for them both. Now, when ions dissolve and dissociate, they're going to create ions. When molecules dissolve, they're not going to dissociate most of the time. Now, I also want to throw this out as an aside. We also have to be able to recognize the ions that we've memorized, the polyatomic ions. And we can't just rely on the idea of spotting when there's a metal attached to some nonmetals. Here's a good example for why. Consider ammonium sulfate. Ammonium is going to be the NH4 plus group. Sulfate is the SO4 double minus group. And these are going to stick together to create a solid at room temperature. When we drop them in water, the ammonium and the sulfate are both going to dissolve and dissociate into the NH4 plus ions and the SO4 double minus ions. But notice there are no metals anywhere in this. All of these are considered nonmetal atoms. So if we rely on recognizing nonmetal and nonmetal as being covalent and metal to nonmetal as being ionic, we're going to have a real problem. We've got to be able to recognize these larger polyatomic ions very quickly. We also have to recognize when they aren't going to be ions at all. Like this one, we might recognize OH as being OH minus. When we think that it might be something that dissolves and dissociates, what we have to do is look at the other remaining chunk and say, is that something that it would be likely to be stable? So if I were to write the ions for that, we'd write CH3, we'd have OH minus, that means it's going to be CH3 plus, and if you draw a Lewis structure for that, you'd see that it's not going to be a very stable thing. I'm not expecting this to exist at all, and that means these aren't going to be things that dissolve and dissociate. They weren't behaving as ions, they were behaving as something covalently bound to each other. So, covalently bound, not going to dissociate. Can dissolve, but will not dissociate. That's a key thing to recognize. So make sure that you're very good at identifying things that are polyatomic ions and being able to determine whether or not they're acting as an ion, or if it's something that happens to look like an ion but won't be. So make sure you can spot those.